All right, so now we're going to venture on, going into chapter 4, and we're going to be looking at clinical radiation generators. So in other words, if we're going to be treating with radiation, how do we produce it? And what are the types of machines that we have at our disposal? Nowadays, you're definitely going to be looking at using primarily your 6 MVs, 15 MVs, 18 MVs, maybe even 25, depending on where you are. And you're also going to be looking at protons as well as electrons. In many cases, most of the machines that we're going to be discussing here don't penetrate anywhere as deeply into the body. But these are still a good history as far as what was used and what has been common in the past. So it's a good review here. So obviously we're looking to in radiotherapy maximize and make the dose uniform within the tumor volume and minimal dose to the normal tissue or organ at risk. Hit the target, try to hit nothing else, even though we know that we're going to strafe a little bit of the other structures that are around it. So the successful radiation therapy treatment is going to depend on the ability of the radiation generating equipment. In other words, you got to have something that's going to generate that kind of dose. So what's it going to be? Well, here is an example of somebody, 1896. What do they look like 70 years later? You're definitely going to want to make sure that you've got that beam targeted in the right spot and that you don't have too many issues otherwise. So beam modification, compensators, things of that sort, blocking the important non-effective surrounding tissue as much as possible is something we need to focus on. So what are the requirements here for clinical radiation generators? Well, we're going to need high particle energy in order to get the particle to have enough energy to penetrate through the patient. We're going to need a lot of them, and that's where the high particle flux comes from. In other words, we're going to have a number of particles going through a particular area there. So in order for us to be able to generate a sufficient dose rate, that's what we're going to need. Energy efficient, obviously we would like to be able to produce this effect without consuming a large amount of electricity. Otherwise it becomes cost inefficient, which can run into problems with the clinic. We'd like for it to be compact, obviously not too expensive, something that's reliable, something that's simple to operate, and something that is safe. Not asking for much, are we? So where did all of this come about? Well, let's see, 1895, we have Röntgen discovering X-rays, and then in 1913, we have Coolidge developing vacuum X-ray tubes. In 1931, we have Lawrence developing a cyclotron. In 32, we have one MV, Van de Graaff accelerator, and is installed in Boston. 39, we have the first medical cyclotron for neutron therapy in California. 1946, a 20 MeV electron beam therapy there at Urbana in Illinois. Progress on a little bit longer to 52, we've got the first Cobalt 60 teletherapy units in Saskatoon. It's a nice word to say. So in 56, we have the first 6 MeV linear accelerator in Stanford. In 58, we have the first proton beam therapy going on in Sweden. In 59, we have the first scanning electron beam therapy in Chicago. In 76, we have the first pion beam therapy in New Mexico. And 1990, we have the first hospital-based proton therapy unit in Loma Linda. So we've come a long way throughout the century there. So what type of radiation generators do we have? We have the KVP, radiation therapy units, Van de Graaff accelerators, we have Betatrons, we have Microtrons, we have linear accelerators, Cyclotrons, and radioactive source-based therapy units. So, kilovoltage therapy units. Photons are generated by hitting a solid target with electrons via Bremsstrahlung interactions, which we covered in chapter 3. The electron energy is below 300 keV, or the acceleration potential is smaller than 300 keV. So the photon energy spectrum is in fact pretty broad. So we put in some filters there to harden the energy. In other words, we're going to take out some of the stuff that's not going to do anybody any good. And those are typically made of aluminum or copper. The beam quality is expressed as half value layers, or HVLs. And that's going to be defined as the thickness of a specified material that would reduce the exposure rate by half. That's why they call it a half value layer. So high skin dose and sharp decrease of depth dose distributions are the major limitations of low energy machines. They just don't penetrate that deeply. So a conventional transformer is used for up to 300 kV, and resonant transformer units are used for higher energies. All right. So here we have the type of machine, the energies that it produces, and then we have the treatment depth, or 90% depth dose. So you can see there the Graaff radiotherapy is less than 20 kV. Nothing there to remark on as far as the treatment depth. Contact therapy, endocavitary, 40 to 50 keV with 1 to 2 millimeters, 90% depth dose, so that's not a lot. Superficial therapy is a little bit deeper, and orthovoltage is a little deeper than that. And then you get up to supervoltage therapy, and then eventually megavoltage therapy. Now you can notice here as the number of volts increases that the treatment depth increases as well. So Graaff's array therapy, 10 to 15 kVp. Graaff's German for border. Gray zone between X-rays and ultraviolet radiation. So that's why they're referring to it as the border, obviously. Close to superficial in construction, and half value layer is going to be expressed in millimeters of aluminum. So now let's look at contact therapy. The accelerating potential is 40 to 50 kilovolts. Tube current is 2 to 5 milliamps. SSD is about 2 cm. Beam hardening by a half to a full millimeter aluminum filter. And it's useful for tumors not deeper than 1 to 2 millimeters. So we've got a superficial therapy unit. We can see that we're a little bit higher than what we have been before, 50 to 150 kV. Half value layer, as you would probably expect, is increasing as well, from 1 to 8 millimeters of aluminum. The aluminum for beam hardening, with some copper included, is 5 to 6 millimeters are added, or a half to a millimeter that is inherent. For applicators or cones for field collimation, as you can see there in the bottom right hand corner. SSD is about 15 to 20 cm, so not very far. Tube currents 3 to 8 milliamps, and it's useful for tumors confined to about 5 millimeters of depth. So you can see there the summary, the FSD 15 to 20 cm, like we discussed before. Focal spot is 4 by 4 millimeters. A beryllium window, along with the collimators included. Cooling system of water, oil, forced air. Got some cones that go along with it. You can see the different sizes there. Good for endocavitary, and the absorption process is going to be photoelectric. So you can see here, you've got your filament, you've got the electron stream coming over here, bouncing off, producing the Bremster lung, focusing them out this way. So you got your useful X-rays here. And this is going to be your beryllium window here. Got the glass envelope surrounding it, cathode over here, anode over here, all that kind of stuff. You're probably pretty familiar with that by now. So you can see here that you've got a 100th of a millimeter of aluminum, and you can see that all of these have a depth of 100% right on the surface. You don't have to go very far in order to see this thing start to degrade. Just watch the beam degrade. And it's not that much of an increase in the amount of aluminum there. Same thing here. Got something with 2 millimeters of aluminum up to 4 millimeters of aluminum, depending on your focus to surface distance. And you can see the depths, and you can see that at least here in this particular range, you can start to see where you still have some remaining dose going deeper into the patient. So you've got the make out here of your contact therapy device. I don't know if you've ever seen these or not. These are keloids, developed after surgery, but this is the clinical use for contact therapy to try to deal with these particular issues. Hypertrophic disorders, degenerative disorders, Dupuytren's, that's referring to a situation where your hand is contracting, the muscles continue to contract, and sometimes the contact therapy can help with that. You can see malignant superficial lesions, basal cell or squamous cell carcinomas, mycosis fungoides, scar lesions, and the like. So what are the advantages and disadvantages? Advantages here are limited penetration to underlying tissues. In other words, if you have something on the other side of the tissue, it's more than likely not going to receive any kind of dose. And part of that's because of the rapid fall off. So the disadvantage is that you've got a high output if you do not filter it. You've got limited penetration into subcutaneous tissues, and cables from the equipment limits movement of the tubes. So what are some NRC regulations regarding these devices? Well, in the on position, the leakage radiation at a distance of 1 meter should not exceed 1 Rankine per hour. The leakage radiation through the tube housing should not exceed 1 Rankine per hour at a distance of 1 meter in the on position. The unit needs an exposure control device to terminate exposure after a preset time. And interlocks are not needed if the KVP is below 150. Filters shall be constructed so that the escaping radiation cannot produce an exposure of more than 1 Rankine per hour at 1 meter. If this radiation is likely to strike the patient, then the exposure shall not exceed 30 Rankine per hour. Changeable filters are used, then an indicator will indicate if the proper filter is in place. And the unit shall have positive indication that the machine is energized. Got to calibrate it monthly. You've got removable cones that shouldn't transmit more than 5% of the useful beam. You've got closed circuit TV or monitoring device is required, and during the treatment, the patient must be in the room by themselves. Okay, so let's move on. So here we have superficial and an orthovoltage unit. So superficial therapy treatment units. Again, we're back to Green's ray therapy, 10 to 15 kV, the gray zone between X-rays and ultraviolet radiation. It's close to superficial in construction, and the half value layer, of course, is expressed in millimeters of aluminum. So here's an orthovoltage unit, 250 kV unit circa 1940. You can also see it there in 1910 for a TB treatment. It's interesting. I didn't really understand that they were used for TB at all. Orthovoltage therapy or deep therapy. So we're looking at energy potential of going to 150 to 500 kV. The beam current is going to be 10 to 20 milliamps. The inherent filtration here is 2.2 millimeters of copper. Focal spot is going to be 5 by 5. Half value layer is 1 to 4 millimeters of copper, but it varies depending on the energy used and the added filtration. And there you can see the different filter types. For orthovoltage therapy, you have the SSDs is anywhere from 30 to 50 centimeters. The window is going to be thin graphite or beryllium. Obviously, your tube efficiency, you're looking at roughly around 1%. Absorption is going to be photoelectric. Collimation system, cones of various sizes, and the dose rate, depending on the parameters, could approach 1,000 centigrade per minute. And routine therapy is generally several hundred centigrade per minute. The application, the tumor is located less than 2 to 3 centimeters in depth, normally for palliation. The limitation of the treatment, skin dose, depth dose distribution, increased absorbed dose in bone, and increase in scattering. So the advantages of orthovoltage is that you get good absorption in the bone, decreased exit dose, and a better percentage depth dose than superficial therapy. But what are the disadvantages? You have less percentage depth dose or less PDD than cobalt 60 units, and multiple ports are necessary due to the lack of penetration and skin dosage. In other words, you can divide it up a little bit from different angles, different parts of the skin. You can sort of, you wouldn't have to have it all coming through at one spot. The NRC regulations are that leakage radiation in the on position shall not exceed 1 Roentgen per hour at a distance of 1 meter. Removable cones or diaphragms shall not transmit more than 5% of the useful beam. A filter shall be constructed so that the escaping radiation cannot produce an exposure of more than 1 Roentgen per hour at 1 meter. Changeable filters will have an indicator that the proper filter is in place. So the device is required to indicate the production of X-rays is taking place. Interlocks are required. locking device to prevent unauthorized use of equipment. It's supposed to be tested monthly. Machines will be calibrated monthly to within plus or minus 2%. You've got to have a means of observation, and lead rubber, lead foil shall not transmit more than 5% of the useful beam. So you can see the depth dose curves right here in front of you. Okay. So supervoltage therapy. Now we're getting closer and closer to the megavoltage therapy. Energies here are basically 0.5 to 1 MV or 500 to 1000 kV. Conventional transformer systems were not suitable for producing potential of greater than 300 kVp. And the problem was solved by the invention of the resonant transformer. Voltage basically was stepped up in an efficient manner. Okay, so what do we have here? Resonant transformer units used to generate X-rays from 300 to 2000 kV. And so we've got freon gas for insulation. So you've got our cooling water here to help with the target. You've got the X-rays coming out. You've got the filament with the electrons going along here, and you've got a focusing coil. And then you can see the plates along here that are helping this thing stay the course until it gets over here to the target. So roughly 1939, there's your 1000 kilovolt machine. So this is a look at your first megavoltage radiotherapy units. Those are some big ones, weren't they? All right, megavoltage therapy. This is the kind of stuff that you guys will be doing when you get out of school. So you got X-ray beams of energy. They're greater than 1 MeV are considered to be megavoltage. Accelerators are gamma ray produced by radionuclides. Examples of clinical megavoltage machines, you've got the Van de Graaff generator, you've got a linear accelerator, you got a Betatron, Microtron, Teletherapy units such as Cobalt 60. Van de Graaff generator, always fun to play with. So you can see there, you've got voltage down here at the bottom. You got some sort of charged comb here that is producing a positive charge, which is going up here and accumulating on this metal sphere. And it's part of the reason why this guy's hair is doing what it's doing. So the Van de Graaff machine is an electrostatic accelerator designed to accelerate charged particles. So in radiotherapy, the unit accelerates electrons to produce high energy X-rays, typically at around 2 MV. In this machine, a charge voltage of 20 to 40 kV is applied across a moving belt of insulated material. A coronal discharge takes place and electrons are sprayed onto the belt. All right, so you got your dome here. You've got your charge collector here, putting it out there. You got your filament, charge sprayer. So you've got the electrons that are carried to the top where they are removed by a collector connected to a spherical dome. So you got them going up here, got the collector, it's pulling those charges over here. And so as the negative charge collects on the sphere, you've got a high potential is developed between the sphere and the ground. So the potential is applied across the X-ray tube, and it consists of a filament, a series of metal rings, and then your target. And the rings are connected to resistors to provide a uniform drop of potential from the bottom to the top. So basically charge gets created here, or it gets stripped off, carried up the belt, collected over here on the dome. Got some connection here to a filament, which is causing these electrons to fire across. And what you have here are several different focusers that focus this in to hit the target, and then you get the X-rays out of that. All right, so here you got your Van de Graaff generator. X-rays are produced when the electrons, of course, strike the target. They're capable of reaching energies up to 25 MV, and they're limited only by the size. It requires high voltage insulation, a mixture of nitrogen, CO2, and sulfur hexafluoride. Van de Graaff and resonant transformer units for clinical use are no longer produced commercially. They've been superseded by the linear accelerator, which this is what we've all come to expect when we walk into our therapy rooms nowadays. Not so much a Therac 20, but something that looks like those. So the linear accelerator, or Linac for short, is a device that uses high frequency electromagnetic waves, or 3000 megahertz, to accelerate charged particles such as electrons to high energies through a linear tube. The high energy electron beam itself can be used for treating superficial tumors, or it can be made to strike a target to produce X-rays for treating deep-seated tumors. So low energy photons, anywhere from 4 to 8 MV, straight through beam, a fixed flattening filter, or in some cases flattening filter free, depending on where you, what is commissioned at your site. External wedges, which I don't know exactly how common that is anymore. There's a lot of EDWs out there. Basically the wedges, by taking the jaw and moving it across the enhanced dynamic wedge, where the jaw moves across the field at a certain rate. But some places may still use those hard wedges that are external. There are advantages to that in planning. You've got symmetric jaws sometimes, single transmission ionization chamber, isocentric mounting. For medium energy photons, 10 to 15 MV in electrons, you've got the bent beam, you've got a movable target and flattening filter, scattering foils, you've got dual transmission ionization chamber, and electron cones. High energy photons, 18 to 25. You've got dual photon energy and multiple electron energies, achromatic bending magnet. You've got dual scattering foils or scanned electron pencil beam, motorized wedge, asymmetric or independent collimator jaws. High energy photons and electrons, you've obviously computer controlled operation, dynamic wedges. You've got EBID and you've got MLCs. So what are the components of modern Linacs? So they're usually mounted isocentrically, And the operational systems are distributed over 5 major and distinct sections of the machine. You've got the gantry, you've got the gantry stand, you've got the modulator cabinet, you've got patient support assembly, treatment table, and then you've got the control console. Okay, so if you were to take all of these components that were just mentioned, and you kind of just drew pictures as opposed to looking at what an actual setup might be, you've got the power supply, so you got the power coming in, you've got the modulator, you've got the magnetron or the Klystron, got the waveguide system, and you got the electron gun, fires it down, you got the accelerator tube, you got a bending magnet, and which then leads into the treatment head, or it goes straight into the treatment head with a straight beam. Kind of depends on the design. So here is one design that has a lot of these components already in there. Grid, anode, you got your electron gun, vacuum pump, you got steering coils, accelerating waveguide, you've got the pulsed electric beam, and then you got the quadrupole magnet, which turns at 270 degrees down this way. Then it can come in and it comes to the exit window. You've got a primary collimator, you've got a dual ionization chamber here. Actually here, you've got the flattening filter here, upper and lower jaws, whether or not you've got MLCs, kind of depends on how it's planned. And then you've got the beam central axis and the couch rotation axis coming out this way. And then you've got the patient laying here on the table. So there's a lot going on here. So let's take a look. Another one of those pictures have shown up. All right, so what are the beam forming components of this linear accelerator? So the main beam forming components of a modern Linac are going to be grouped into 6 classes. You got the injection system, RF power generation system, you've got accelerating waveguide, you've got auxiliary system, and you got beam transport, beam collimation, and beam monitoring system. Boy, that looks like 7 components, doesn't it? So the injection system, this is the source of the electrons. It's usually a simple electrostatic accelerator called an electron gun. You got 2 types of electric gun that are used as sources of electrons in medical Linacs. You've got the diode type and you've got the triode type. So the electrons are thermionically emitted from the heated cathode, focused into a pencil beam by a curved focusing electrode, and accelerated towards the perforated anode, through which they drift and enter into the accelerating waveguide. So the radio frequency power generation system, the microwave radiation used in the accelerating waveguide to accelerate electrons to the desired kinetic energy is produced by the RF power generation system, which consists of 2 major components. You've got an RF power source and you've got a pulsed modulator. So the RF power source is either a magnetron or a Klystron. Both are devices that use electron acceleration and deceleration in a vacuum for the production of high power RF fields. So the magnetron is a device that produces microwaves. So it functions as a high power oscillator, generating microwave pulses of several microseconds duration and with a repetition rate of several hundred pulses per second. It's a cylindrical construction, has a central cathode and an outer anode with resonant cavities machined out of a solid piece of copper. Okay, so we can see the magnetron here. Copper block, we've got a glass dome here, we've got our transmission waveguide down here, and we can see the filament connections, output waveguide, turning knob, cooling water connections, peripheral cavity, as well as a cathode. So the electrons emitted from the cathode are accelerated towards the anode by the action of the pulsed DC electric field. So under the simultaneous influence of the magnetic field, the electrons move in complex spirals towards the resonant cavities, radiating energy in the form of microwaves. The generated microwave pulses are led to the accelerator structure via the waveguide. So typically, magnetrons operate at 2 megawatts peak power output to power low energy Linacs, 6 MV or less. Although most higher energy Linacs use Klystrons, accelerators of energy as high as 25 MeV have been designed to use magnetrons of about 5 megawatts of power. So you can see the pulses of radiation. You can see the electron gun voltage pulse, Klystron voltage pulse, and the timing pulse. So the Klystron is not a generator of microwaves, but rather a microwave amplifier. So it needs to be driven by a low power microwave oscillator. So the electrons produced by the cathode are accelerated by a negative pulse of voltage into the first cavity, called a buncher cavity, which is energized by low power microwaves. Okay, so you got low level microwaves to be amplified, so produced here in some fashion. You've got a hot wire filament, cathode, you've got the electron streams boiling off of that. So you've got your first cavity or your buncher, and then your second cavity or catcher. So you've got the electron bunches coming down here, the drift tube, and then eventually these electrons will hit here, and you're seeing the amplified high power microwaves being emitted out here. So another way to look at this is that you've got your filament here, you've got your focused thermionic cathode, got your cylindrical focus coil, you got your electron bunches, and then you've got the collector down here. Got a ceramic RF window where you've got the rectangular transmission waveguide here. Okay, so how does it work? So you've got microwaves are being set up, or microwaves set up an alternating electric field across the cavity. This velocity of the electrons is altered by the action of this electric field to a varying degree by a process known as velocity modulation. So some electrons are speeded up while others are slowed down, and some are not affected. So that results in bunchings of electrons as the velocity modulated beam passes through a field-free space in the drift tube. The electrons suffer a deceleration, and by the principle of conservation of energy, the kinetic energy of the electrons is converted into high power microwaves. So waveguides are evacuated or gas-filled metallic structures of rectangular or circular cross-section used in the transmission of microwaves. The length of the accelerating waveguide depends on the final electron kinetic energy and ranges from around 30 cm at 4 MeV to 150 cm at 25. So two types of waveguides are used in Linac. You've got the RF power transmission waveguide and you've got the accelerating waveguides. So the accelerating waveguide, you've got the power transmission waveguides transmit the RF power from the power source to the accelerating waveguide in which the electrons are accelerated. The electrons are accelerated in the accelerating waveguide by means of an energy transfer from high power RF fields, which are set up in the accelerating waveguide and are produced by the RF power generators. So the simplest kind of accelerating waveguide is obtained from a cylindrical uniform waveguide by adding a series of discs or irises, circular holes at the center, placed at equal distances along the tube. The discs divide the waveguide into a series of cylindrical cavities, and these form the basic structure of the accelerating waveguide in the Linac. So you've got two types of accelerating waveguide have been developed for the acceleration of electrons. You've got the traveling wave structure. It requires a terminating load at the end of the structure to prevent the reflected wave. And you've got the standing wave structure, produces maximum reflection on both ends when combined with the forward wave and forms the stationary wave. Okay, so waveguides. Okay, so for waveguides here, we have a traveling wave, which is something that moves in one particular direction as it goes along, even though the medium itself is probably staying put. And then you've got a stationary wave where you have nodes and antinodes, nodes, antinodes forming in order to be able to have a wave that looks like it's not moving at all. So traveling waveguides. So in a traveling wave structure, the microwaves enter the accelerating waveguide on the gun side and propagate towards the high energy end of the waveguide. These guides have relatively low shunt impedances compared to the standing waveguide systems. They need to be physically longer to achieve the same output energy. Electrons from the gun end enter at a velocity of 80% of the speed of light, 80 kV, and that's pretty quick. So relativistic dimensions here should be taken into consideration. After the first 30 centimeters, they're traveling at velocities close to the speed of light. This first part of the guide is called the buncher section. Thereafter, further energy gain results in a relativistic mass increase, and the iris separation remains constant. So you can see here the bunching sections. You got the electrons as they come in. But in a traveling waveguide, only 1 in 4 cavities is at any given moment suitable for electron acceleration, providing an electric field in the direction of propagation. So in the standing wave structure, each end of the accelerating waveguide is terminated with a conducting disk to reflect the microwave power, resulting in a buildup of standing waves in the waveguide. In this configuration, at all times, every second cavity carries no electric field and thus produces no energy gain for the electrons. So cavities serve only as coupling cavities. Can be moved out of the side of the waveguide structure, can effectively shortening the accelerating waveguide by 50%. Low energy Linacs, the target is embedded in the accelerating waveguide, and no beam transport between the accelerating waveguide and target is required. Bending magnets are used in Linacs operating at energies above 6 MeV. So the accelerating waveguide is usually mounted parallel to the gantry rotation axis, and the electron beam must be bent to make it strike the X-ray target or be able to exit through the beam exit window. So you've got choices here. You've got 90% or 90 degrees of bending, 270 degrees bending, which is referred to as achromatic, and 112.5 of the slalom bending. So electrons moving in a magnetic field are bent in a trajectory dependent on the energy of the individual electron. The requirement for the generation of satisfactory clinical beams, electrons shall exit from the accelerating tube within a small focal spot and at the correct angle. The electron beam at the input to the bending chamber is going to be very narrow energy spread, and electrons will automatically flow or follow the same trajectory. So precise control of beam energy is going to be difficult to achieve. So the more stable solution is to design a so-called achromatic bending system. Electrons of different energies exit at the same point and in the same direction in spite of their having followed different trajectories. So 270-degree magnet using hyperbolic pole faces. So more energetic electrons, larger radii, enter closer spaced regions with higher bending fields. Less energetic electrons encounter lower bending fields between the wider pole spaces. All electrons that entered on axis at 0 degrees should converge again at the same point at 270. And the deflection is without dispersion with energy. It's achromatic. The Linac head contains several components that influence the production, shaping, localizing, and monitoring of the clinical photon electron beams. So looking at the 4th and the 5th generations of machines, we've got several retractable X-ray targets, flattening filters, and electron scattering foils or scattering filter, primary and adjustable secondary collimators, dual transmission ionization chambers, a field defining light, and a rangefinder, optional retractable wedges, and optional MLCs. So we can see here in the head, you've got the electron beam coming out here, you've got the X-ray target, primary collimator, you've got the flattening filter or scattering foil, depending on what's on the carousel as it goes around. You've got the ion chambers here, you've got secondary collimation, got a slot for wedges, blocks, compensators, what have you, and then you've got the flattened X-ray beam. You have an electron beam. There's some things that change here. You're going to have the scattering foil here present in the beam as opposed to the flattening filter. But if the rest of this really does look very close to the same thing. All right, so what do we have going on here in the Linac treatment head? We've got electrons originating in the electron gun. No surprise there. They are accelerated in the accelerated waveguide to the desired kinetic energy, then brought in the form of a pencil beam through the beam transport system into the Linac treatment head. This is where the clinical photon and electron beams are produced. So, clinical photon beams are produced with the target flattening filter combination. Clinical electron beams are produced by retracting the target and flattening filter from the electron pencil beam. and either scattering the pencil beam with a single or dual scattering foil. So the primary collimator defines a maximum circular field, further truncated with an adjustable rectangular collimator, which is probably what we're more used to. It consists of two upper and two lower independent jaws, producing rectangular and square fields and maximum dimension of 40 by 40 at the Linac isocenter. And it's that limiting dimension which can cause all kinds of fun problems. So the dose monitoring system. IEC specifies in detail the standards for radiation monitors installed in clinical electron Linacs. It deals with standards for the type of radiation detectors and display of monitor units. So what are the most common dose monitors in Linacs? You've got transmission ionization chambers, permanently embedded in the Linac clinical proton and electron beams, and monitors the beam output continuously during patient treatment. Sealed ionization chambers are they are response independent of ambient temperature and pressure. So two separately sealed ionization chambers, independent biased power supplies, and readout electrometers. The secondary chamber will terminate if the primary fails. Additional dose of only a few percent above the prescribed dose. The Betatron was the first electron accelerator used for radiotherapy in the early 1950s. It's an electron in a changing magnetic field experiences acceleration in a circular orbit. Can produce a wide range of energies, less than 6 to more than 40 MeV electrons, low electron beam current or low dose rate, and that's a smaller treatment field. So you've got your donut tube here, you've got your electron orbit, you've got the filament, you've got the injector, the deflector, as well as the target. The Microtron is a combination of a Linac and a cyclotron. The electrons attain higher energies by repeated passing through the Linac component. Final treatment beam can be extracted at different orbits positions for different desired energies. So you've got your waveguide here, you've got the electron gun, and then you've got the bunches coming around, and then eventually they move through the deflection tube. You've got the extracted beam that comes through, and then boom, you have your useful beam right there. You have the cyclotron, developed in the 1930s at UC Berkeley. It's also got the Ds. That's generally how a lot of people remember it. So the alternating potential is applied to the Ds, which are back to back, and we'll see that in a minute. Charged particles are accelerated as they leave one D and enter another D. Particles travel in circular orbits due to the magnetic field. With increased energy, the radius of the orbit also increases, and cyclotrons are used for protons and neutron machines. So these are the Ds. You can see 1D right here, and then you can see the backwards D over here. You've got the high voltage, high frequency oscillator here. You've got the ion source, and you've got the deflector, and then you've got the target. So you can see the inner workings of it. See a picture of it there. So what are the medical applications of a cyclotron? It's going to be used to generate high energy protons and heavy ions for therapy. It's used to accelerate deuterons to produce neutrons, and it's used for the production of radionuclides. So it's used in PET. So you've got radionuclide of radium-226, you got cesium-137, you got cobalt-60, and then you can see all of the relevant scientific data that comes from that. So you got your radium-226 here, you've got cobalt-60, and then you can see the decay scheme here of your beta minus decays, where 99, even greater than 99% of the time, what you're going to see here is a decay to this level, and then you'll see decays all the way down here as it turns into nickel. There is a 0.1% chance that your decay will come here, and then you will just see this being released. Most of the time, you're going to see not only this released, but also this. So a typical cobalt-60 source is a cylindrical disc of diameter ranging from 1 to 2 cm. This will give rise to geometric penumbra. Interaction of the primary gamma ray, the source itself, and other surrounding materials in the treatment field. So you have low energy contaminants, and it contributes to about 10% of the total intensity. So if you look inside here, you can see your source, see the source capsule, you can see the field light, primary definer, mechanical source position, collimator rotation scale, optical distance indicator, all of these kinds of things. This is how the cobalt machine would actually work. So you have your cobalt-60 source, you have your tungsten cylinder, enriched uranium, and then you have lead. So outside of that, you have your laser source, and then you've got the collimators here, and then the gamma rays come out. So for the source housing, it's housing for the source. It's called the source head. A steel shell filled with lead for shielding purposes, and the device for bringing the source in front of an opening in the head while the useful beam emerges. So the heavy metal alloy sleeve provides an additional primary shield when the source is in the off position. So a number of methods have been developed for moving the source from the off position to the on position. Source mounting on the rotating wheel inside the source head carries the source from the off position to the on position. The source mounted on a heavy metal drawer, plus its ability to slide horizontally through the hole running through the source head. In the on position, the source faces the aperture for the treatment beam. In the off position, the source moves to its shielded location, and a light source mounted on the same drawer occupies the on position of the source. So, solid cylinder discs or pallets contained inside a stainless steel capsule sealed by welding. This capsule is placed into another steel capsule, which is again sealed by welding, and double welded sealed is necessary to prevent any leakage of the radioactive material. So the source head consists of a steel shell fixed with lead, a device, typically a pneumatic device for bringing the source in the front of an opening while the beam is on. The beam is on, so you've got the source moving from here into here so that you can actually expose what you want. So all of the above mechanisms incorporate a safety feature in which the source is returned automatically to the off position in case of a power failure. The last thing you want is for it to remain out there. if you don't want it there. Beam collimation and penumbra. So a collimator system is designed to vary the size and shape of the beam to meet the individual treatment requirements. The simplest form of a continuously adjustable diaphragm consists of two pairs of heavy metal blocks. Each pair can be moved independently to obtain a square or rectangle shaped field. Some collimators are multi-vane type, in other words, multiple blocks to control the size of the beam. And the term penumbra, in a general sense, is going to mean the region at the edge of the radiation beam over which the dose rate changes rapidly as a function of the distance from the beam axis. So in other words, you have a source here that's coming along, and if you're over here, you're going to see the collimator, of course, try to block a lot of the stuff that's coming through, but it can't block all of it. So you might be getting a little bit more exposure here than what you think. And then, of course, as you move over here, you're in the way of the rays coming from the source. You can see how these collimator blocks are shaped such that you can try to reduce this less than useful amount of penumbra here, so that you have a straighter edge through which this can cut. So you've got your source here, which is a certain width, your source to skin distance, and then you can see here that the jaws are blocks, have this action going on trying to cut down on the stuff that's being transmitted, but you can see the edge or the stuff that's emanating from the edge of that particular source coming down this way. And then from this other side, you can see it kind of crossing this way. So you can see that even if we go through and we try this particular arrangement, you can still see that there's some sort of penumbra going on here where we can get some exposure here, but not quite all of it. So to reduce the geometric penumbra, trimmers can be used to increase the SSD, which you'll notice here, if this goes up, then your geometric penumbra here is going to be affected because you've got a larger number here in the denominator. So the penumbra width increases with an increasing in the source diameter, which you would expect. That's also why it's up here. SSD and the depth. SSD and the depth. Oh, and I think I said SSD here when I should have said SDD. So in the penumbra will decrease with an increase in the SDD. Geometric penumbra is independent of the field size as long as the movement of the diaphragm is in one plane. In other words, the SDD stays constant with an increase in the field size. Heavy particle beams, these particles include neutrons, protons, deuterons, alpha particles, negative pions, and heavy ions. They have the advantage in terms of dose localization and therapeutic gains, and greater dose on tumor than on normal tissues. High energy neutron beams may be produced by DT generators, cyclotrons, Linacs, and nuclear reactors. So you can see some of these neutrons being produced here in these reactions. The major advantage of high energy protons and other charged particles is the Bragg peak, which is this right here in the depth dose distribution. So particles with the same MeV over A have approximately the same velocities and range. So for example, 150 MeV protons, 300 MeV deuterons, and 600 MeV helium ions have approximately the same range in water, about 16 meters. Negative pions of energy close to 100 MeV have been used in radiotherapy, providing a range of 24 cm in water. The Bragg peak exhibited by pions is more pronounced than other heavy charged particles because of the additional nuclear disintegration by pion capture. That's called star formation.